Thank you very much for having me in this vibrant workshop. So today I'm going to talk about the leptogenesis and dark matter coming from myelin. So this work is based on these two papers. So first let me give a brief overview of this work. So we are thinking of type 1 seesaw, where the Yuan lepton or Yuan Biman global lepton symmetry or Biman symmetry is spontaneously broken. So that as a consequence of this, we have pseudo-Galton boson, which is called the myelin. So most of the time we will use this variable theta defined by the myelin mass divided by its decay constant, or the VEF of the symmetry breaking. So this is this neutrino quark coupling, and then there is this Yuan Biman cell breaking field. So then we will introduce additional Yuan symmetry breaking, soft breaking term, which will give us the myelin mass. So basically we are assuming some Zn symmetry instead of global Yuan symmetry, so that from this potential we'll get the myelin mass like this, and then so after symmetry breaking, this myelin will couple to the fermion field in this way, so it will have derivative coupling. So if we look at this zeros component, theta dot component, so theta dot couples the charge operator. So in the background, the non-vanishing of theta dot in the medium, it will break Cp and T. So that can be a source of so-called leptogenesis in our framework, a la Cohen-Kaplan. So actually, this scenario revived recently by the work of Cohen, the collaborator. So they asked whether this mechanism can be applied to the action. So actually, they found that it can give a right baryon symmetry, but it cannot have a dark matter at the same time, because in the action case we have a tight relation between decay constant and action mass, right? So either you have usual the action dark matter scenario, or you can have assuming some non-vanishing theta that in the QCD action you may generate baryon symmetry. Also, this cannot be compatible to each other. But in our case, of course, this myelin mass and decay constant is free parameters. So yeah, you can find some parameter range where both leptogenesis and dark matter can be satisfied at the same time. So here, having initial theta dot, so we can from that equivalently we can set some initial value of theta dot number. So depending on the myelin mass term, okay, so actually the baryogenesis temperature is almost the same as myelin mass term of the right hand neutrino. So I mean, okay, so from this formula, assuming some initial value of y theta dot, you generate a right number of baryon symmetry, and then this theta y theta dot also gives you the right dark matter density if you have appropriate value of mass. So this is the overall picture of our scenario. So let us go to some details. Okay, so first, we know that the usual misaligned mechanism. So initially we assume some misaligned value of theta, And then, of course, when the Hubble parameter become comparable to the mass itself, it will start to oscillate, right? Then at this time, the non-vanishing value, I mean, the CDM we have oscillation of theta and theta dot, and then we will have energy density, and this is, indeed cold dark matter. Realized by this very light scalar field, so that was the mechanism used for QCD action to generate right dark matter density. So now, instead of initial misalignment value, so we can also assume some initially misaligned, initial kinetic motion, non-vanishing theta dot from the beginning. Then this is theta dot energy density. Then energy density of this theta field will be theta dot squared. So there will be some kind of theta dot dominated universe. So it's kind of kinetic motion, kination domination. So this energy density will scale down to the t to the 6th. Okay, theta dot scales as a t cubed. So then for initially large theta dot energy density will decrease as a t to the 6th as the temperature cools down. And then it will meet this own potential, then it stops to the potential, and then follows the usual kinetic misalignment mechanism until the Hubble parameter becomes comparable to the mass itself. So then this is a usual. Then you will have usual kinetic misalignment mechanism. But the assumed theta dot was very, very large. So initial rho theta was very large. Then it will go like it will evolve like a t to the 6th. Then this kinetic energy meets the potential when the Hubble parameter is larger than its mass. So at the later temperature, it can hit its potential. So then at this moment, it will immediately oscillate to give CDM density. So in our case, our parameter space, we will use this kind of possibility, so that so in this region we can have both baryogenesis and dark matter genesis at the same time. Okay, so to give you a brief introduction of how this spontaneous baryogenesis works. So as I said, okay, so if there was a non-vanishing theta dot in the background, actually, it copies the charge operator, so it behaves like a chemical potential of the fermion. Namely, it shifts energy density, energy of the fermion. So if positive for a particle, negative for antiparticle. So this is definitely CP vibrating background. Also, this is the background is given. So in this case, our baryogenesis mechanism is different from usual thermal leptogenesis or baryogenesis. Because for this mechanism to work, this kind of chemical potential should be fed into the thermal field of quarks or leptons. So that for this to occur, we need some B violating or lepton violating operator should be in equilibrium. So then finally, we can generate a non-vanishing chemical potential of the quarks or leptons proportional to theta dot. And then at the end of the day, okay, so baryon or symmetry will be generated when this baryon or lepton vibrating operators goes out of equilibrium. At that time, this relation will be freezing, so that we will get finally baryon or symmetry, which is proportional to the theta dot at that moment. Okay, so in CISO, I mean, we have this usual, okay, so type 1 mechanism. And then, actually, in this case, we have right-hand neutrino decay or inverse decay, which is obviously lepton number violating. So that in this case, this process can be in equilibrium. Both processes can be in equilibrium within certain mass range. So temperature, between, say, for instance, temperature 0.1 times the mass of right-hand neutrino, and then temperature, say, 10 times larger than the right-hand neutrino mass. So, in this period, our lepton number violating is in equilibrium, and then we can fit theta dot in the symmetry of the quarks and leptons. Okay, so yeah, this is basically okay. So so we already explained this. Okay, so to see this, okay, so I mean during my lecture, we introduced this K number. So the decay rate of right-hand neutrino divided by Hubble parameter calculated at the temperature of the right-hand neutrino mass. So if this K number is very large, say, then this decay and inverse. So this is a decay, and then this is a plot of inverse decay. Oh, we didn't come to this yet, but anyway. So this the decay rate normalized by Hubble parameter will be decay and inverse decay will be both in thermal equilibrium, meaning the rate divided by Hubble parameter larger than 1 during some period. So for typically we take K equal to 50. So then this interaction will be in equilibrium, both in equilibrium between the range which I mentioned. So say 10 times the mass or 0.1 times the mass. So okay, so then in this case, okay, so as we did in usual thermal leptogenesis, so the Euclid couplings are in thermal equilibrium, so we have a thermal equilibration condition, and then in this period at the same time, this the neutrino Euclid coupling interaction is in equilibrium through decay or inverse decay. So then okay, so we can, the right-hand neutrinos are Majorana particle. Basically, you can treat them as I mean, it's a Majorana particle, so its chemical potential can be put to be 0. I mean, in reality, it's a bit more tricky, but practically we can take this option, so that here this equilibration condition of this coupling says that the theta dot contribution should fit into this equilibration equation. So that's how we can get non-trivial contribution, I mean chemical potentials of the quarks and leptons, and then at the end of the day you will generate baryon asymmetric quantity like this. So baryon asymmetric quantity is given, determined by theta dot at this temperature. Okay, so in this way, I mean, okay, so after some calculation, you get the allowed parameter space in terms of Majorana mass, and then decay constant. So basically, okay, so the region in white is allowed. So in this region, okay, so actually we can put some initial theta dot. I mean, so initial theta is our free parameter. So we don't care about the origin. So if you are able to generate appropriate theta dot, then in this range, we can generate baryon asymmetry and dark matter at the same time. So a lot of parameter space, say, I mean, for Majorana mass, say, K from KV down to 10 to minus 5, 6, 7, 8 electron volt, or decay constant, say, should be around the 10 to a few times 10 to 6 GeV, and then should be smaller than, say, 10 to 13 GeV. So above this line, I mean, usual misaligned mechanism works, and then typically we produce too much dark matter. And then in certain cases, right-hand neutron mass can be even smaller than the electroweak scale. So that in this case, baryogenesis temperature should be the electroweak scale, where Falloran process freezes out. Okay, so then we can ask ourselves, what can we just start with initial misalignment, not from initial theta dot put in the soup. So in this case, you know, this starting from non-vanishing theta, and then theta dot will be generated around Hubble parameter equal, I mean, when Hubble parameter is around this mass, right? So in this case, we have a maximum theta dot, but this oscillation is coupled with the oscillation of a theta. So it is impossible to get right value of theta dot generating baryonic symmetry. So then we came up with an idea that if symmetry is non-restored in the early universe, so our the lepton number breaking field can couple to Higgs or any scalar field in the thermal equilibrium. So we can achieve some negative value of it. Then we can get negative mass, temperature squared mass. So symmetry can be broken even at high temperature. So then at high temperature, the Majorana mass can have a negative, I mean, it's a large contribution from this coupling. So that means our decay constant is also temperature dependent in this way. And then Majorana mass also temperature dependent. It's higher than the vacuum mass. But it scales down very, very quickly. So Tc is the temperature when this temperature mass is comparable to the zero temperature mass. So when above Tc, the Ft increases as T, and then the Majorana mass increases like T to the n minus 2 over 2. So in this case, okay, so the brief history of the whole quantity is this. So at high temperature, at certain temperature, the temperature-dependent mass can be compared to Hubble parameter. Hubble parameter is also proportional to T squared. And then there is oscillation. There is first oscillation starts when the temperature mass is compared to the Hubble parameter. Then later, when temperature drops down, the mass itself becomes much smaller. So this is the behavior of the mass. So the mass decreases faster than the Hubble is, faster. And then as soon as this oscillation occurs, the kinetic term scales like T, but mass term scales much faster. So basically, we can realize kination domination right after the oscillation. So they start to decouple. So from this period to Tc, so they will have theta dot dominance. So then we can actually forget about in this evolution equation, you can forget about this mass term because this mass term and the potential energy is much smaller than the kinetic energy itself. So basically, we have this kind of evolution. So kination dominates. So theta dot scales like T instead of T cubed. Okay. Good. So then at Tc, temperature dependence disappears. Then theta dot, again, as usual, scale like T to the cube. So then say the kinetic energy decreases, and then it can hit, the kinetic energy hit to the potential barrier, so the oscillation starts. So we can have usual dark matter generation at this point. So without this, I mean, this Hubble parameter, yeah. Okay, so then we can basically, the right-hand neutron mass could be somewhere here or somewhere here, so that we can generate correct baryon symmetry. Okay, so these okay. So some more detailed explanation, and then let us skip. So so this is the parameter range where we can have baryon symmetry and dark matter genesis in a right way. Starting with this misaligned mechanism in symmetry non-restoration framework. So, but here the thing is that the required parameter range is quite ad hoc. I mean, you know, lambda mixing coupling is around 10 to minus 10, and then the quanticoupling of the symmetry breaking field should be very small. So, yeah, basically lambda phi, the quanticoupling should be around, typically around lambda mix squared. So if we arrange these such small couplings, actually we can generate right genesis of baryon and dark matter at the same time. So because of this property, actually our Majoran field, yeah, typical range of our Majoran field is around the electron volt, and then the decay constant is around 10 to 6 GeV. Also, having such a small quanticoupling, the scalar field of the scalar pattern of Majoran field is also very light. It should be around MeV region. So actually, Higgs can also decay to this light particle, but it turned out that the mixing coupling is also small, so this invisible decay of Higgs, in our case, cannot be that large. So it cannot be seen at collider for our parameter range. Okay, so I discussed this, how this baryogenesis and dark matter genesis can be achieved in type 1 CSO, or if you have a Majoran in our field. So I mean, we worked out, so this is non-symmetry restoration mechanism, we worked out for some specific value, but we are thinking of extending this study to higher dimensional operator. Also, this mechanism also can be applicable to type 2 or type 3, whatever system mechanism you have. So that would be also interesting direction to go. Thank you.
Okay, let's thank Professor Chun. Any questions?
That first.
Hi. Yeah, very nice talk. So I have a doubt. So you showed Klein-Gordon equations, and there you had term like phi double dot plus 3h phi. So you had this FA term, extra FA term there. So I missed that. So could you again? Yes. No. So if you go to next slide. Yeah, this one. So you have this term here. So usually in, so could you explain this term again?
Okay, so I didn't. Well, You start with the usual field. I mean, theta is normalized by A over FA. FA is temperature dependent, right?
Yes.
So that was why
So because I'm asking this because if you just consider axion field, for instance, then if we just consider the axion field,
Okay.
so the Klein-Gordon equation for that is just 3h5 dot.
Yeah, that's right. Okay,
Yes.
yeah. Sorry,
Yes.
I didn't mention this. Okay, in terms of A, it's A double dot plus 3H A dot.
Yeah, exactly. But
Yeah, but now since we have this temperature dependent part of FA, so this will, actually this will give me minus 2H. So this friction is H, not 3H.
I see.
That was why we have this behavior theta dot proportional to temperature.
Okay.
Okay, thank you very much.
Thanks.
Yeah. Cos-
Axion field.
this is a,
Very much similar to the relaxion.
yeah.
Right. So will you have a cutoff when on the Higgs mass also?
Cutoff on Higgs mass.
So
I no idea. I don't know. I mean,
in the relaxion, you take the mass of the Higgs to be as large as the cutoff, and it gets settled in the massive, what do you call that, oscillation period.
okay,
And they couple the
so
Higgs to that.
yeah, that's right. So you are saying relaxion, maybe relaxion can do the same job.
It's the same job, and I don't know if it works for the fermion. What I mean by the Marana mass for the
Well, okay, couple the relaxion to the fermion, then it works.
Right.
Okay, maybe that may work. Okay, yeah, let's try to see whether. Yeah. I don't know. Yeah, good. Yeah, okay. Yes.
Is there, I'm just curious, this is outside this whole thing. Is there an exact solution for that? I'm just curious, have you,
This is, yeah.
there are exact solutions for this?
One can think so. Okay, I can say so.
Okay.
I mean,
without the damping, I know there are exact solutions.
yeah,
So
we.
No, it's just curious. I'm just curious. It's not related to this.
We did it.
Yeah,
I mean,
yeah.
we actually solved it numerically.
Numerically.
Yeah. I mean, the whole plot. Yeah.
I think he's asking if there's an analytical form for the solution.
Oh, is that right?
I'm asking.
Oh, you're asking me? No, I don't know. I mean,
Without the damping, it is the electric function.
yeah, maybe that will be interesting. No, we. Yeah, I tried the numerical solution. Then no, yeah, we can talk about that. Thank you. Okay, thank you.